Okay, hello. This is the theory for chapter 10, which is it's just a continuation of chapter 9. It's again about impulse and momentum. So, yeah. Last chapter we covered conservation of momentum, right? But we're just going to get into a more in-depth analysis about that. So the thing I was talking about at the very end, like all the collisions and stuff, we are talking about that more in depth in this video. So we use the word impact to describe that collision, right? So this is used to describe particle interactions. So if you throw a ball, there is going to be impact there because you've interacted with a particle. If you hit a ball with a baseball bat, right, there's going to be impact between the bat and the ball, right? So this is specifically, there's also when large forces are produced, right? So like if you like poke something really weakly, it's probably not going to be an impact, right? There wasn't any like a large force at all. So there are two types of impacts, right? We have a central impact and oblique impact. So a central impact is when the velocities follow the line of impact, right? So if we imagine ourselves two balls like this, we're going to have a line of impact between them. And when the velocities, which are represented by these arrows, are on this line, that is going to be a central impact. So central impact velocities are along line of impact, right? And then an oblique impact is when the velocities are angled. So here's the line of impact down the middle. Maybe your velocity is here and here, offset by an angle theta and an angle phi, right? This is a disgusting theta, by the way, so let me fix that. There we go. Offset by an angle theta and an angle phi. So velocities are at an angle with line of impact, which is LOI. So those are the two types of impacts, and both will come up in questions. So it's important to make the distinction. Central impact, obviously, easier calculations, right? So from chapter 9, we have M1 V1. Oh, that's not supposed to capitalize. M1 V1 is equal to M2 V2. I mean, not equal to, plus M1 M2 V2 is equal to M1 V1 prime. V1. Wow, I really messed up that. Okay, really miswrote these like this, plus M2 V2 prime, like so, right? So in chapter 9, we had three things that were known. This would be like for the problem videos, right? You'd have three knowns, so you'd probably have the masses and like some velocities known, and then an unknown. So now in chapter 10, we have two unknowns, right? So you could have two velocities that are unknown or something, right? So there are going to be several things that happen now, right? So firstly, when particles collide and there are deformation forces that are produced on, we can call this ball 1 and ball 2. So there are deformation forces produced on 1 and 2, and they are equal and opposite, right? So at maximum deformation, they merge together and travel at the same velocity. And that's what I was talking about earlier in chapter 9, where I mentioned the M1 V1 plus M2 V2 is equal to M1 2 V1 2. That's that formula. And then 3, there's restitution, right? And this is going to be a new formula. So restitution occurs. So restitution occurs is one of the new things that happen, right? And before that, we just have collision produces forces, and then maximum deformation force equals a, I guess you would have learned this in high school physics, or at least I did, like the name of the impacts. I don't remember though. I think it was an elastic collision. No, that's not right. Anyways, is equal to sticking together after collision, right? So now we have the restitution occurs. So particles try and return to their original dimensions and push each other apart, right? And then they travel to their final velocities. So the coefficient of restitution is what is actually going to help us with the fact that we have two unknowns in our equation, right? So restitution, we use lowercase e to represent it, is equal to the final velocity divided by the initial velocity, right? And if we wanted to put this into a formula, we'd go delta VF over delta VI, where F is final, I is initial, right? So it's the difference in the final velocities divided by the difference in the initial velocities. So that is what the coefficient of restitution is. And this is a description of the relationship between deformation and restitution, where, again, restitution is when they try to return to their original dimensions, right? So with the coefficient of restitution, right, we can now solve for if we're missing two of our two variables. If we have two unknowns, right? So since this is a value like this, and also keep in mind that E is always between 0 and 1, right? So it's always positive, and it is between 0 and 1 at all times. So on to the next part. We're going to just keep elaborating on restitution. So when E is equal to 0, right, this is a perfectly, I forgot a colon. This is a perfectly plastic collision, right? So that means that there is no restitution at all. And when something is perfectly plastic, they stay together after collision. So ball 1, ball 2 collide, and now they become two things, and they go off this way, for example, right? That is a perfectly plastic collision. So plastic meaning the particles stay together after impact, right? And when E is equal to 1, this is a perfectly elastic collision, right? Elastic means that the objects restitute, so they will go back at the same velocities. At same means same velocity afterwards, right? So what that means is, like, if you think about it, right, 0, that means delta VF is equal to 0, right? And if you think about it, if they stick together as one object, well, velocity of object 1 after is equal to velocity of object 2 after, which is equal to velocity of 1, 2. So if you do velocity 1, 2 minus velocity 1, 2, you get 0 on top. And now if they stay exactly the same, if we have velocity 1 equals velocity 1 prime and velocity 2 equals velocity 2 prime, if we have velocity 1 prime minus velocity 2 prime divided by velocity 1 minus velocity 2, we're going to get 1, right? And remember, it's always positive. So work and energy, right? We cannot use these to analyze the details of the impact because we don't have the magnitudes of deformation and restitution and the displacements. So that's easy. Solving for central impacts is also very easy because we have our two equations, which is sum of the momentum initial equals sum of momentum final and the coefficient of restitution. So that's easy. We don't have any angles or anything. It's straight lines. These two hit each other and then they bounce back this way, for example. We have everything we need to solve that. Coefficient of restitution, everything. So we're going to be looking more at oblique impacts now because these are what is considered, these are what we consider the difficult impact analysis, right? So if we were to consider this these two velocities, and then these two balls collide, and then they go off like this at these velocities with a line of impact down the center like this. Well, we have 1, 2, 3, 4 angles, right? And we have 1, 2, 3, 4 velocities. So we have 1, 2, 3. We have 8 unknowns. Like, we can assume we know the masses. We have 8 unknowns here, alongside the coefficient of restitution, right? So if we have the coefficient of restitution, could we solve this? Well, let's think about it. This angle and this angle are linked to these velocities, so we can get our we can split it into components, our x and y's. We know that the sum of the momentum in x has to equal the sum of the momentum final in x, and same thing for y, right? So we can simplify this into x and y components, and then we have our coefficient of restitution also in x and y components, right? So it could be possible, right? So the thing is, for oblique impacts, is deformation and restitution only occur along the line of impact, right? So like, if it's not along the line of impact, there's going to be no change at all, right? So that means it simplifies it even further down to, in this case, just x, because the line of impact is in x. So that means your momentum in y stays completely constant, and your momentum in x is what changes. So that's when you would plug in your m1 v1 equals m2 v2, or whatever. m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v1 prime v2 prime in x, and then coefficient of restitution in x, and you would use these to solve for solve for whatever you're missing, right? So this is the line of impact, so L for line of impact. And if I just switch colors here quickly to red, this is horribly drawn, I know, but this is the point of contact. And the point of contact, so in this case y, the components remain unchanged. So that is the theory here, that along a point of contact we have no change in our momentum, and along the line of impact we have restitution and deformation, which means we're going to have a change in the momentum. So that is pretty much it. So when you're solving a question, you're going to look for two things, right? You're going to find your line of impact, and you're going to find your point of contact. So along the point of contact, we have velocity doesn't change. And if velocity isn't changing, that means momentum isn't changing, because momentum is mass times velocity. And velocity, as we already know, mass, as we already know, is always constant. So velocity doesn't change. And along the line of impact, we have restitution alongside conservation of momentum, right? And that is how we solve these questions when we're looking for whatever unknowns we might be looking for. Maybe we're looking for the angles. Well, for that, you need your velocity components. We're looking for velocity. For that, you need your velocity components. You're just solving for velocity and like angles, right? So that leaves us with, in terms of questions, there are 3 steps to solve, right? So 3 steps to solve problems. So firstly, we identify the impact type. It's either central or oblique, and then it's either plastic or elastic. That's what it means by that. So we either have, identify if it's plastic or elastic, and if it's oblique or central. Okay, and then you identify the unknowns, and identify what you know. Identify unknowns and knowns. And then, so we can do state diagrams. So that's basically just drawing the initial and final positions. I'm going to be honest, I usually skipped this step. when doing questions. So when I do the problem solving video, I will not skip this step if I don't need to. But yeah. And then 4 is list the variables for your equations. So like if you have all your velocities, you could list them out and then recognize that you have the coefficient of restitution given to you, right? Maybe you're solving for massive object 2 in this scenario and you have all your velocities and like, I don't know, you're missing one more thing, whatever, an angle or something. There you go. That's 2 unknowns. So then you list your variables, match them up to the equations, and it's easy as that. And then final step is just solve, right? I don't know why I said 3 steps to solve. This is supposed to be 5. That's just like the fact that I can't count apparently. So that's very fun. Lost my ability to count. Anyways, so, and keep in mind if E is 0, so if the coefficient of restitution is 0, you probably don't need the equation other than like at like a theoretical standpoint where it's like, oh, I know that this is a plastic collision, right? That's the only thing you need your coefficient of restitution for is, oh, I know that this is plastic. So like, let's go. Good for that, right? So anyways, that's all there is for chapter 10. It was just a continuation of impulse and momentum from chapter 9. Thank you for watching. Hope you learned something. Bye.